still looking at the Jupiter-Europa system, and this is the induction of currents in Europa's ocean due to its motion in Jupiter's magnetic field. The Jovian magnetic field, approximately 150 nanotesla. Europa's orbital period is roughly 3.55 days. That should be days. So that's going, and its distance to Jupiter is changing, so that the Jovian magnetic field is going to have an amplitude, a variational amplitude that we're approximating as 150 nanotesla. And this will induce electrical currents in Europa's ocean, and flyby spacecraft have measured a deviation in the magnetic field believed to be due to induced currents in Europa's ocean, and this is one of the reasons that it's believed that Europa does have a liquid water ocean underneath the ice surface here. The ocean depth is roughly 100 kilometers, so we can perform this simulation also in QuickField. And once again, I have an axial symmetric model of Europa. And we're just going to assume that the Jovian magnetic field is only has a z direction at the moon here. So let's look at the problem properties. So this is AC magnetics, very low frequency, as we're moving around Jupiter. And it looks at some of the block labels. Before we just meshed the ice, so this is actually the same dimensions as before. I'm choosing kilometers as my length units here. The interior, the ice has a conductivity of a very small 10 to the minus 7 s per m. The interior region giving it a conductivity of 0.1 s per m. The ocean will give it a conductivity of 0.5 s per m. And this is the vacuum region, so we'd have no conductivity, just unit permeability. Okay, let's look at some of the edge labels here. Now, I need to simulate a uniform magnetic field here at Europa, and in order to get the required strength, I'm assigning a magnetic potential of something like 1.8 megawebers on the side. Okay, I have zero normal current defined at these boundaries. So we're going to have zero normal current between these interface. And there's zero tangential magnetic field here. So we have a uniform field that's flowing along the z direction, horizontal to the page, zero normal current at the ice boundaries and so forth. Okay. And at the planet. Now, I'll go ahead and solve the problem. It's already been solved. This is roughly 33,000 nodes. And we can look at the results. Okay, so we have a color map here. So the Jupiter's magnetic field is purely z-directed at the location of the moon here, and we can see the current density flowing, and we can look at its peak value and so forth here. So we have a peak value of the current density near the equatorial region that I can look at with the my selection tool here. Okay. Also, we can make a contour plot of the current density, perhaps as a function of depth inside the ocean. Which is roughly 10 to the negative 7 amperes per meter. If we like, we can animate the solution. And look at the field at various phases. Notice we can look at the quadrature phase and see the magnetic field solely due to the induced currents in Europa. So I'll stop the animation and I'll go back to the picture properties, and I want to look at the field lines at 90 degrees out of phase. Okay, let's zoom in here a little bit. Remove this. So this would represent the magnetic field that's just due to the induced currents flowing in Europa, since we're looking at 190 degrees out of phase with the Jovian field. The final simulation, I want to look at a thermal conduction in spherical bodies. For example, the Earth or Europa, or if we have something like an asteroid that's differentiated, we don't have to actually mesh the entire spherical region. We can actually look at a wedge of that and save computation space. And I'll show you an example of that. Okay, and this simple geometry I've constructed is simply would be a spherical region. However, I've just made a pie-shaped element here to save space. And so the problem is a steady-state heat transfer. Once again, we're in axial symmetry. So we have an iron inner core and a silicate rock exterior region. So many asteroids and bodies in the solar system that have cooled have differentiated where the heavier metals will sink to the bottom, or to the center in this case, if we're in space. And however, there will be some heat generation due to the radioactive decay of aluminum and other radioactive elements. So I've given this a thermal conductivity of 7. Okay, this is for the rock region. And for the metal, has a higher thermal conductivity of roughly 68 watts per meter Kelvin. And now I've included a volume power of heat source. So this volume power of heat source can be due to the radioactive decay. And we have a boundary here. Okay, so this is the outer boundary of our planetesimal with 100 Kelvin. This edge, we're giving 0 normal heat flux because we have spherical symmetry. We don't expect the heat flux vector to be normal to this boundary. In fact, I could make the wedge smaller if I like and give it 0 normal heat flux condition. Now, I have put a radiation boundary condition on the interior metal part of the body here, and it has given an emissivity of 0.9. Okay, so we can go ahead and examine solution. Okay. And we can zoom in to see the temperature profile and also plot the temperature as a function of radius from the center. Okay. So the interior, roughly 60,000 K. All right, and then it attenuates very rapidly inside of the silicate region. Okay. So that concludes the astrophysical simulations and the geophysical simulations. For more examples of both types of simulations, I've included in the biophysics textbook, as well as the applied electromagnetics using QuickField and MATLAB, both by Jones and Bartlett Learning.